Hello everybody once again. Welcome to the first video on Mechanics Chapter 9. So we're going to have a look at constant acceleration in this chapter, but at the start we're just going to derive the basic ideas and recap hopefully what you know from GCSE Maths and indeed GCSE Physics. Now this lesson does have a prerequisite. It's got something here I want you to do before the lesson itself, which I hope I've mentioned to you if I've seen you before. And it's this. It's not a big thing, but it is crucial. So what I want you to do before the lesson, if you're watching this remotely, is this preparation task. So first of all, some reading and note-taking. The table on page 121 of the Statistics and Mechanics book, and the notes and examples in there from page 122 to 124. Also as well, I'd like you to make some notes on the vectors, page 125, and then read and copy up example 6 and example 7. And so this preparation task is from chapter 8 of the book, which we're not going to cover in full in lessons. There's enough in the book, and the book does it very well. There's enough there to give you a grounding for what you need in this chapter. So absolutely have that done first and foremost, because it will be crucial to your understanding of what comes next. So before we get started with the stats and mechanics, there's a few warm-up questions for you to have a go at. Here they are, 1, 2, 3, 4, as usual. So pause the video now and attempt these yourselves. When you're ready to see the solutions, press play and we'll go through them together. So without further ado, let's have a look and see if we can solve question 1. Question 1 of the warm-up. We have here an object which is starting from A and travels to the right to B, then back through A to O, and then back through A to stop at B. So that's quite a bit of information, and so before I even attempt the question, I'm just trying to get that straight in my head. So let's just break this down piece by piece. So it starts from A and travels to the right to B. So I'm going to do that as the first step. So first of all, what's happening? I'll just draw a line on to denote what's going on. We're starting at A and going to the right to B. Then we go back through A to O, and so what does this mean? So back through A to O means we're going to go this way from B back to O. And then finally we go back through A to stop at B. So the final piece of this is we're then going to go back through A to stop at B. So the final bit is basically go back to B once again. And so in order, this is like step 1, then step 2, and finally step 3. We've ended up over here. So for A, we need to find the final displacement of the object. And so on the top of your notes, there's a definition of what displacement is. So I'm just going to share this with you again, in case you're not sure or you've missed reading this. So displacement is a vector quantity. It has a size and direction. And the length of it is the shortest distance from the initial position to the final position. And so in this question, the initial position just means where the particle started at. So it started from A, and so that's the starting position there. The final position, because it stops at B, the final position's here. So it started at A, and it's gone to B, and so therefore the final displacement is going to be 5 meters to the right. So it's going to be a positive 5 meters. It's gone to the right of A, so the displacement's 5 meters. The final position of the object is obviously at point B. The distance between its starting and finishing points, that's also 5 meters. Okay? The size of the distance between the starting and finishing points is the same as the displacement. Now, the distance may have been 5 meters if, for example, it had finished at O. And if it had finished at O, the displacement would have been -5 because it had been 5 to the left of its starting place of A. Because, however, it finished at B, it's positive 5 metres. It's 5 metres to the right of B. Now D, the total distance travelled by the object, well, as you can see in the first step, it goes 5 metres from A to B. It then goes back through A to O, so it goes along this red line, which is 10 metres back. And then it goes along this green line back through A to stop at B, so it goes a final 10 metres to get back to B again. So 5 plus 10 metres, the total distance it's travelled is 25 metres. And so, if nothing else, question 1 is meant to give an illustration of how displacement is totally different to distance. They're often confused because they use the same units, but they are different concepts. Displacement is just a measure of the final position relative to the starting position. Question 2. Given that the object in question 1 takes 4 seconds to complete its journey, find, for part A, the average speed of the whole journey in meters per second. Well, we need to remember how to work out average speed. It's a formula. So average speed is simply distance travelled divided by time taken. Okay, so what we can do here is just plug in what we had from before. The distance it travelled was 25 metres. The time taken, we're told, is 4 seconds. And so if we did 25 divided by 4, we'd get 6.25, and the SI units, the standard international units, are metres per second, ms to the -1. So that's the average speed. For part B, we need to work out the average velocity, which is something different altogether. So average velocity is very similar in terms of how the formula looks. But rather than at the top being distance travelled, the top is simply change in displacement. It's the rate of change of displacement instead of the relative change of distance. It's the rate of change of displacement, I should say, rather than the rate of change of distance. It's still divided by the time taken, so that bit of the formula is the same. So the change in displacement for part 1 was just 5 metres, and the time taken, again, 4 seconds. So 5 metres divided by 4 seconds, that gives 1.25 metres per second. So as you can see, clearly not the same thing as the distance. Sorry, it's clearly not the same thing as the speed. Question 3. So the diagram below shows a straight line graph. Find the gradient of the graph. If you're thinking, why am I asking you to find the gradient? It's just to try and get your confidence up. If you can find the gradient, you're going to be able to work out certain properties of speed, distance, and time relations. It just boils down sometimes to what the gradient means in some circumstances. So here, the gradient, as you should know, is just the change in y divided by the change in x. So for this one, y goes from 0 up to 21. X goes from 0 to 7, so that's 7. So the gradient is just 3. Finally, for question 4, find the gradient of this one. So again, it's not really any harder, only a very tiny bit. The gradient, again, is going to be the change in y divided by the change in x. So the change in y this time is a tiny bit of working out, but barely worth mentioning. Okay, so the change in y here, we're looking at just this bit, from 25 to 5. So 25 minus 5, the change in y is now just 20. because it's not starting from 0. X is starting from 0 though, so the change in X is just simply 10, that's easy. 20 divided by 10, that gives us a gradient of 2. Let's now go on and mention some of the basics of this chapter. So this isn't going to be too arduous, it's a fairly short video by my standards. The main bit is just giving you the grounding for the harder stuff which will be following. So let's start off by talking about displacement time graphs. The motion of an object can be represented on a displacement time graph. So displacement is always plotted on the vertical axis and time is always plotted on the horizontal axis. Displacement depends on time, and the independent variable, as ever, is plotted horizontally. So the independent variable is time, that goes on the x-axis, as it were, the horizontal axis. So in displacement time graphs, S represents the displacement of an object from a given point in meters, and T represents the time taken in seconds. This is a tiny bit misleading, very, very tiny bit. It says here S represents the displacement of an object in meters and T represents the time in seconds. You could do a displacement time graph in different units, for example miles per hour or kilometers per hour, but almost always it will be meters per second, because like I said in the warm-up, meters per second is the SI unit for both speed and velocity. So a few different examples of what displacement time graphs tend to look like. So the first one, completely flatlining. So S versus T, T versus S is just completely flat. What would that mean? This would mean that there's no change in the displacement over time. It's not going up or down, and so that just means the object is stationary. If you have a displacement time graph looking like this, the object is not moving. What if it looks like this? If a displacement is going up at a constant rate, if it's a straight line graph? Well, in this case, the displacement would be increasing at a constant rate over time, and the object is moving, therefore, with constant velocity. Finally, what if we had something like this, where the displacement was going up as a curve? Okay, that would mean that the displacement is increasing slowly at first, but then the rate of increase is itself increasing. So the displacement would be increasing here at a greater rate as time increases. What this means is velocity itself is increasing, and so therefore this would model acceleration. If you have a displacement time graph where it's curving upwards, or curving downwards in fact, that would show what acceleration looks like. So let's just finish off quickly with a worked example. So we have a cyclist riding here in a straight line for just 20 minutes. She waits half an hour, then returns in a straight line to her starting point in 15 minutes. The diagram shows the displacement time graph of her journey. So part A, work out the average velocity for each stage of the journey in kilometers per hour. So as you can hopefully see here, there's 3 main stages. Okay, so the first stage is from the origin up to A. So let's do that for part A. What about stage OA? So here we're just working out average velocity. Okay, so average velocity, I'm going to use shorthand here, V equals change in displacement divided by time. For displacement, as we go from 0 to A, it's gone up from 0 to 5. It's gone up by 5 kilometers. And that's taken her 20 minutes. Now be careful, we want this in hours. Okay, so actually what I'm going to do here, and this is optional, you could work it out after if you wanted. What I'm going to suggest we do is to actually just write down here what these minutes are in terms of hours. So 10 minutes, that's 1/6 of an hour. 20 is 2/6, that's 1/3 of an hour. 30, that's half an hour. 40 is 2/3 of an hour. 50 is 5/6. 60 is obviously 1 hour, and 70 will be 7/6 of an hour. So here, the velocity is change in displacement, which is 5, and the time in hours, if we just read down from here, you can see the time taken is 20 minutes, which is 1/3 of an hour. So 5 divided by 1/3 gives us 15 kilometers per hour. And that's how. Let's now have a look at the next stage from A to B. Now this stage is very simple indeed. If you recall from what we said earlier, if it's a flat line going completely horizontally, this means that the velocity is 0. The displacement is not increasing. So for this one here, the velocity is 0. So we've got so far a velocity of 15 kilometers per hour for the first bit, and for the next bit a velocity of 0 kilometers per hour. Units aren't as important here. A velocity of 0 is going to be 0 no matter what units you use. But anyway, may as well include them, I suppose. Final stage, we're going to go back to where she started. The final stage is from B down to C. So stage BC. We've got here that the velocity is the change in displacement divided by time. So here we need to be slightly careful. In this case, the displacement is going to be negative because we're going towards the origin, not away. So we were 5 kilometers away, now we've gone back to 0, and so the displacement is minus 5 kilometers. Now at this stage, we need to estimate the time here, because as you can see, at the point C, it's between 60 and 70. So we need to be thinking here, roughly, don't need to be too worried about guessing wrongly, just be as accurate as we can be. I'm going to go for that's about 65, about between 60 and 70. I mean, you could argue it's maybe 66, maybe it's a bit over halfway. It doesn't typically matter too much. I'd say maybe 66 minutes. I'm going to plump for, I think, 65. So because I'm plumping for that being 65, after a slight bit of deliberation, 65 minutes there, between 50 and 65, that's the time taken to go from B to C. So what we need to think about here is from 50 to 65, that's actually going to be 15 minutes. So the time taken is 15 minutes, which is a quarter of an hour. Okay, so the time taken here is going to be 1/4 of an hour, 15 minutes. You could, if you wanted, work out in kilometers per minute, then convert to kilometers per hour. That's another way you could do these as well. Anyhow, minus 5 divided by a quarter is the same as minus 5 multiplied by 4, so we get minus 20 kilometers per hour. She goes home quicker than what she travelled away from home. Or starting point, anyway, it might not be home. Part B, it says now to work out the average velocity for the whole journey. Now this is something of a trick question, however this would likely be a 1 marker in an exam. 1 markers should always get you thinking. There might be an easy way of doing this, and indeed there is. Average velocity It's for total change in displacement divided by time. So just take a step back and think, for this whole journey, what's the total change in displacement? She starts at the origin, she returns and finishes at the origin. She's actually travelled a net distance of 0, so there's no change in displacement. You can divide that by anything you want, as long as it's not 0, of course, that'd be naughty. So 0 divided by 65 minutes, so 0 divided by, what's that going to be in terms of hours? So it's going to be, that's 6/6, 6.5 over 6. It's going to be 13 over 12, whatever you want really. This bit's optional, to be honest. It's going to be 0 meters per second. Because she's not moved anywhere from where she started, she's returned directly to it, so the net distance travelled, the net displacement from the starting place is 0. Part C, now this is a different question altogether. Work out the average speed for the whole journey. So for part C, the speed is going to be the total distance travelled divided by the time taken. Okay, so I meant over 12 there, by the way. So distance travelled divided by time taken. So what I'm going to do here, I'm going to add up that 5, that's nothing, then another 5, so it's 5 plus 5. Okay, and the time taken is 65 minutes, so in terms of hours, that's 65 divided by 60. And I think I worked that out right. Cancelling by 5s, you get 13 over 12. But what you should do, and I'm not practicing what I'm preaching, is use a calculator here. So let's just do this here. So it was on binomial mode, I'll get off that one. So 5 plus 5, which is 10, divided by 65 60ths. So we get here to 3 significant figures that the average speed was 9.23 kilometers per hour. Now it might be worth you thinking, is that right? Because it seems much lower than these two here, but just recall from the earlier parts that actually she had stopped for a significant portion of this. Between A and B, for half an hour she stopped and didn't travel anything. So that's what brings down her average speed considerably. So that's all there is for me on 9.1. It's now over to you to try some of these on your own. So what I want you to do here is all of 9A, there's only 4 questions, mind, on page 132 from the Stats and Mechanics book. But please remember as well, what I really want you to do, if you're not done already, is this. So if you've not done already, please make sure you've done the preparation task and that it's fully complete. So just to recap what I mentioned at the very beginning, reading and taking notes from the table on page 121, all the notes and examples from 122 to 124, vectors notes, page 125, and then read up and copy and digest examples 6 and 7 as well. That'll stand you in good stead for the rest of this chapter. Thanks very much again for listening. Do try that exercise. If you struggle, you know where I am. And anyway, I'll see you all soon. Please take care.